Hello, everyone. Thank you for joining us for today's Fiber Broadband Association webinar. My name is David Norris. I'm the webinar producer here at FBA. And thank you very much for taking time to join us today. Today's webinar is Tackling the Myths of Micro Cable, and this is being brought to us by Hexatronic. Before we jump into the actual presentation for today, I just want to go over a couple quick housekeeping items. First of all, as attendees, you are in listen-only mode. However, we would like to hear from you and would like to hear your questions. So if you do have a question for our presenters, please type it into the Ask a Question tool, which is located in the lower left-hand side of your screen. Also, please note that there are some resources, including a white paper. It's the first in the list of resources in the upper right-hand side of your screen. That white paper is a good reference, something you can even download while you're on the call here and follow along if you like. But that's a great resource to take with you. There's a number of other resources in there as well, which I encourage you to check out and which we'll reference throughout the presentation. So again, today's presentation is about tackling the myths of micro cabling. And we're joined by the folks from Hexatronic here. We have Mark Turner, who is the Director of Business Development at Hexatronic. And he is joined by Anders Björk, who is the Product and Project Manager at Hexatronic. And like I said, they're going to help us separate fact from fiction when it comes to microcable. And with that, I will go ahead and get out of the way and hand things over to Mark to get us started. So Mark, whenever you're ready, take it away.
Very good. Thank you, David. Appreciate all your support here and help with getting us webinar on schedule today. Thank the Fiber Broadband Association staff for a tremendously successful conference last week, the Fiber Connect conference. All things last mile were discussed there, and I know Hexatronic personally and company-wide had a tremendous value out of that conference. Also, thanks to the attendees, most importantly, and for the FBA membership for last week. This topic today is part and parcel to micro cable systems being able to support last mile fiber to the home system. So it's a very good timing to tie both of those tremendously needed networks in together. I'd like to introduce Hexatronic US here quickly. We are part of the global company Hexatronic Group based out of Sweden. We are in the fiber solutions business. We have several businesses. The fiber solutions are what we're going to talk about today. Hexatronic US manufactures and develops micro cabling, micro duct, and all the required ancillary accessory components that comprise a micro cabling system. My name is Mark Turner. I'm the business development of Hexatronic here in Hexatronic US. Have 30 years in the telecom industry, with the last close to 20 years being in the fiber to the home part of the telecom industry. So have experience in engineering out in the field, systems engineering, designing networks, as well as marketing and sales experience. So thank you for having us on today, and I'll turn it over to my colleague, Anders Björk, at this point to start. He's going to talk about the mechanics of micro cabling systems, and then he'll hand it back over to me in about 15 minutes or so to start on the business case for micro cabling systems. So Anders.
Thank you, Mark. Hello, everyone. I'm Anders Björk, and I've been working with fiber optics since 1989 when I joined Ericsson at that time. It's been for 36 years. I have had positions, among others, as technical manager, head of product management, and I've also been plant manager for a fiber plant. For the last 15 years, I have been working back and forth with the US market. I have also been based in the US. I was based in Plano, Dallas, at the Ericsson head office for a couple of years, and I was based in Lexington, Kentucky for Hexatronic for a couple of years. But I moved back to Sweden 2020 when the pandemic started, and then I've been in Sweden since then. So I will start to introduce microcables. What is a microcable? It's simply a very small cable, typically between 4 and 11 millimeters. It's half the diameter of a conventional cable and about 1/3 of the weight. It has very high fiber density. It can contain up to hundreds or even thousands of fibers. And the installation method used is mainly air-blown fiber techniques. And the myths that we will cover during this webinar, that is, the microcable is not robust enough, and it's complicated to install, and is it a costly solution? This could not be more wrong, and that's what we will show you during this webinar. I will start to present the evolution of the microcable. First of all, a little bit about the fiber optics that started in the 70s and 80s, and the first viable fiber optic cables were developed here in the US by US engineers. And it transformed the telecom industry. I mean, you have now light transmission over long distances with minimal attenuation. So the fiber optics began to replace the copper in backbone networks at that time. It took a couple of years before the development of micro cable started, and that was in the 90s. The urban broadband demand surged, and it was a need for a compact duct-friendly cable, and the micro cable started to emerge, and Netherlands, they was the front runner. They were very early with city networks and fiber to the home networks in Netherlands. Early 2000, the technology spread to Denmark, Sweden, Norway, and Germany, and also to Asia. And we also had, as you can remember, the fiber to the X boom at that time. And several manufacturers, including Draka, Prysmian, and Hexatronic, at that time Ericsson, continued to develop the microcable systems. We at Ericsson, we developed our first microcable at 2006. And today, the microcables are more or less standard. They're used in modern fiber to home and 5G and access networks. And the innovation continues. I mean, the blowing characteristics have been improved. There's higher fiber counts and more robust designs and so on. And they have been used from Arctic extremes to vast expanse of the deserts. We at Hexatronic, we have delivered and used the microcable north of the Arctic Circle in Sweden, Norway, and Finland, and also in deserts in Middle East, for instance, in Qatar and Jordania. We have used them in South Africa, Philippines, etc. Many different climate zones. So then we have the first poll question. Why is a microcable used? You can read the answers there. Okay, continue. I will start to discuss the first myth about the robustness of a microcable. Important here is that we need to compare apples to apples. To look at the microcable system and robustness, you have to treat it just as a system, where the microduct is a very important, crucial component of the system. The microduct is made of HDPE, which is very hard and stiff. It provides a protective and flexible pathway for the microcables. It also shields the cable from physical damage and environmental stress. It's very flexible, meaning that new cables can be blown through the ducts without the need for excavation. Space efficiency, I mean, the small diameter of the duct, it enables high-density cable installations, which is ideal for urban environments and where you have space that is limited. And the microduct comes in many sizes and configurations. And what I will focus now on is that the microduct provides a protective pathway for the microcables. So I will start to talk about pipe stiffness. That is the measure of a flexible pipe resistant to deflection, which is ovalization when it's put under load. And typically, we express that in kilopascal or pounds per square inch PSI. And when you test the HDPE conduit, You put load until you have a 5% deflection of the conduit. And why is that important? It actually ensures that the pipe maintains its shape when it put on load. And it's very critical if you have an underground installation and you have soil and traffic loads, etc., that apply pressure to the duct. And it also helps the engineers to choose the right material for the pipe or a microduct, and also the wall thickness for some specific applications when it's tough applications like underground. So we start by describing the SDR. What is SDR? SDR is a standard dimension ratio, and it's a method of rating a pipe's durability and also the capacity to withstand pressure. And it's defined like this. It's outside the diameter of the duct or conduit divided by the wall thickness. And if you look at a regular 1¼ inch conduit, then the SDR will be around 11. This is a standard conduit. If you look at the microduct, the very typical microduct used in many microduct systems is 14 millimeter outer diameter and 11 millimeter in the diameter. Then you have an SDR of 7. And the important thing is the higher SDR, the thinner pipe walls and lower stiffness, and the lower SDR, thicker pipe walls and higher stiffness. And if you look at this, the microduct has a lower SDR than the conduit, which means it has a higher stiffness. And we can look at some graphs here. If you look at the 1¼ inch conduit, you can see that that one withstand the pressure of, had a pipe stiffness of 60 kilopascal, and the 1410 microduct 100 kilopascal. You can also look at this as PSI. The SDR7 has 2,279 PSI, and the 11 have 492. And I got these numbers from PPI, which is the major North American Manufacturers Trade Association for plastic use in pipes, conduits, and infrastructure solutions. They do research, white papers, etc. And I have been a part of it for a couple of years, and it's a great association, I would say. I wish we had something like that in Europe, but we do not have that.
Anders, there's a pretty good question here that came in. If you can field that for a second here. Is there a standard or a clear definition for what a microcable is?
I mean, there is a standard that describes a microcable. It's an IEC standard, and it's a good question. And also, if you look at Telcordia GR20 standard here in the US, it actually refers to the IEC standard. So yes, there are standards. I will also talk a little bit about the blow-on performance of microcables, starting by describing pulling cables. If you pull a cable, you start by push a rodder through the duct or pipe, and then you attach a pulling rope to the rodder, and you pull the pulling rope through the pipe. And then you attach the cable to the pulling rope, and you pull that through the duct or pipe. And if it's heavy pulls, you can have a winch or something. And you also need these pulleys, as you can see, they have to be used where the cable enters and exits the conduits. If you have manual pulling, you can pull maybe 300 to 600 feet or so. If you have a winch, then you need, first of all, a quite strong cable, and you can pull maybe between 1,000 and 6,000 feet, something like that. And the theory behind pulling cable, I mean, when the cable passes a bend, then the cable will be pushed to the inner side of the bend, and the friction will increase exponentially. And this is called the capstan effect. It will lock the cable to the bends. Knowing about this, and it caused problems, then the blowing technique or jetting was developed. And the theory about air jetting then is you do push the cable, you have a pushing force there, and you do that mechanically. It could be motorized rollers or belts or something like that. And then at the same time, you blow compressed air into the duct, and this reduces the friction and create the pulling force. And then a drag force of air moving along the cable surface distributing the pulling force along the cable length. So it's pulled the cable also through the duct, and the cable will be in the center of the duct when you have bends and so on, so you don't have the same capstan effect as you have when you do pulling. And you can blow a cable between 3,000 and up to 10,000 feet doing like this. And also I want to mention that the cable is not exposed to any high tension at all, because the duct carries the air carries the cable through the duct. The important parameters that affect the blowing performance, for cable is cable stiffness. The cable must be stiff enough to resist buckling, but flexible enough to navigate the bends. And also the fill ratio, which is the ratio between the cable diameter and the inner diameter of the duct, which will affect the airflow, and also the friction, of course. But then you have also other parameter that is important when you install both the duct and the cable. I mean, duct bands and undulations, type of installation tools you use, and the equipment. Okay, we do have a test track where we do standardized test. This test is standardized in this ISC standards, as I talked about before. It's 100 meters per leg, and at each end of the leg you have 2 predefined bend diameters, as you can see on this slide. We have it indoor in the plant, so we have the same consistent parameters, so we can compare different results. We always do this when we have a new cable type or a new duct or something. We test them together. For a micro cable, we tested 2,000 meters, and this tough track is 19 bends then on these 2,000 meters, since every leg is 100 meters. And this is a typical test result from a test like this. We blow, it's a 288 fiber micro cable, diameter 7.9 in a 16-12 millimeter duct. And we start by push the cable in 60 meters per minute until the speed drops to 40 meters per minute. Then we switch on the air and increase speed to 60 meters per minute again. You can see the dip there, that's 450 meters or so. That's where we put switch on the air. And then we continue until we reach 2,000 meters, or if the speed drops too much, down to 20 meters per minute. But in this case, you can see we reach 2,000 meters in around 32 minutes. And these are our fill ratio recommendations for microcables. The fill ratio, that's the difference, the ratio between the cable outer diameter, OD, and the duct inner diameter, ID. We have green light between 40 and 75% fill ratio. That's what we recommend. It's a low risk to fail. It's the best performance. And you also have some buffer for the parameters that we can not control by the product parameters, the installation, undulation, bends, and so on. If you are between 75 and 80%, it's higher risk to fail, but you can still make it if you have a good and right stiffness of the cable and you have a good installation and good tools and so on. We do not recommend to be above 80%. If you look at 30%, if it's a low fill ratio, you can still make it. If you have you need some extra air, and you can also use like a parachute in the end of the cable to help it go through the duct. Another poll question. Which scenario causes the highest risk of installation issues blowing a microcable through microduct? That has been probably proved. Okay, should I push next? Okay. Then I leave the word to you, Mark, then.
Anders, there's one quick question on our micro cable stiffness. Can you kind of just speak to stiffness in the micro cable to get the best blowing performance?
It depends on the route. If it's a long distance and quite a straight route, then it shall be very stiff with no bends. So then that's the best performance you can have, a very straight route. You can blow between 3 and 4 kilometers actually. But if it's many bends, then you need to have it not as stiff than softer. I cannot give a number or so, but it depends on the application, I would say. The more straight, the stiffer you can have it.
But we aim for 2,000 meters blowing distance. That's our goal, is 2,000 meters.
Yes, in a quite tough test bed, yeah. Yes.
Thank you for that. Thank you, Anders. So now we'll go into the business case advantage of micro cables versus traditional, what the industry calls as duct cables. They're all dielectric, just like our micro cables are all dielectric. But that's the comparison we're going to go through here with a 288 fiber micro cable versus a 288 fiber traditional duct cable. And we do, while I'm here, we do have, David mentioned it earlier, we do have a nice white paper where these slides come from if you want to read more of the details about the total cost of ownership and the business case advantage of microcabling systems. As Anders mentioned, it's a microcabling system comprised of the protective thick-walled microducts and then the all dielectric slim microcables. Microfiber cables is what that term is also called in the industry. So this slide here we're looking at, TCO, total cost of ownership. It's a widely known acronym when you're deploying a fiber optic network. The civil works looks like a Pac-Man there eating up the duct and the cable. It's such a big percentage component of the overall cost to deploy a fiber network. And so what that means is there are different installation techniques. You can horizontally, directionally drill microducts in the ground just like you can standard conduits. You can trench, open trench microducts in, or you can vibratory plow them in. Any installation method used for standard conduits is also directly applicable to installing the microduct foundation for the microcabling system. Then you see the next cost component, which is about 9% there. The gray is the actual microduct assemblies. That's a grouping of microducts with the orange sheath, which is direct buried in the ground and has a locating wire in it. And then the next smallest cost component is the actual all dielectric micro cable itself. In this case, so this example, 288 fibers. The range that Hexatronic offers is 12 fibers up to 864 fibers in our micro cables. But what you want to do, since the construction cost is around 80%, the civil works, as they call it, construction costs, that's all the labor hours. You want to make sure that the system is designed properly. So it's essentially a dig once approach where you get the proper number of microduct pathways in the ground for future expansion and future scalability of the fiber micro cables whenever their expansion is needed. We're not going to install all the microfiber capacity year one. That's the typical approach. There may be exceptional cases where you need to do that, but typically you want to put in as many fibers as you need year 1 to year 3, for example, and then the subsequent years of the life cycle over 30 years, keep blowing in more micro cables. So next, there we go. So total cost of ownership optimized system. What do we actually need to accomplish to be able to actually save time and investment money? So techniques that minimize, you're not going to eliminate, but you try to minimize field splice points, field fiber splice points as much as possible, because those take handholds, they take splice cases, and they take labor to make the fiber cables be joined together. All right, so that's what you want to minimize if possible. That's a key advantage of micro cables. You can have those installation lengths being up to 2 kilometers that we mentioned earlier. That's 6,560 feet before you have to do any fiber splicing at all. Even at 2 kilometers, then you can set a hand toll and do a figure 8 on the ground and continue your micro cable blow all the way up to our longest lengths are 8 kilometers for the micro cables themselves. So you want the longest possible micro cable lengths. That also helps with your optical power budget too. It gives you more headroom for your optical power budget when you can minimize these splice points and have the longest install lengths. Lighter weight materials facilitate easier handling and much faster, half the time typically to install the micro cable, at least 50% time reduction versus pulling traditional 288 type fiber size cables through standard conduits such as 1.25 inches. Micro cables, the machine pushes it with the air assist that Anders mentioned, so you can have a couple people versus 4-person crews, for example, because you're not having as much physical manpower to pull the cables through the conduits with standard cables. Transportation cost is a bottom line cost. It impacts basically how much fuel you're burning to get the microducts and the micro cables out to the distribution facilities and then also out to the work sites. And we'll show the comparison of micro cable systems there with transportation cost reduction. And then also the last one is squarely involved in TCO, and it's basically a design optimization over the life cycle of the system being decades. You want to upgrade fiber bandwidth when you need to, instead of having to install all the optical bandwidth year one. There are some very large micro cables out there, even that exceed 864, but the cost of those things goes up as the cable size goes up as well. So incrementally adding additional fiber cables whenever needed is a key part of the total cost of ownership advantage for micro cabling systems. So we've got 2 scenarios here. The first one, you see we have a standard 288 fiber cable there. It's about a diameter there of 18 millimeters, whereas the 288 micro cable is 10 millimeters less in diameter, almost 10 millimeters less. The big thing to note there is 4.5 times the cross-sectional area between those 2 cables. All dielectric cables, apples for apples. So the standard traditional cable requires 1.25 inch conduit or larger, whereas the micro cable requires only a 1612 millimeter duct. So just to equate 1.25 to millimeters, that's about 31 to 32 millimeter is what you need for the standard versus a 12 millimeter inside diameter for the 288 micro cable. So that's the comparison here that we'll look at. So we'll start looking at here the comparison on the right, the same capacity label comparison. So you can see this is a success-based approach where you put in the pathways, either conduits on the left there in the gray or microducts on the right in the gray. You put in the number of pathways you'll need for the life cycle of the system. So on the left, you've got to put in 4.25 inch conduits. In year one, you can pull in the 288 fiber cable. On the right, you see the 4-way 1612. That's basically this overall size of an 1.25 inch conduit. So you blow through the 288 fiber micro cable, and then for subsequent years, you got 3 empty segmented microducts ready to accept additional 288 fiber cables in the future. And on the right, you would be able to pull additional 288 fiber cables in the future. The next cost component is the orange. That's your duct work. And then the smallest component, like we mentioned already, is your fiber cable. So going over to the right-hand side, the details, if you add these numbers up, you're coming out within a open trench scenario, you're coming out to 58% more cost with the 4 conduits and pulling the 4 288 fiber, or pulling 1 cable during the first year versus the micro cabling solution there. So that's most often the one that gets scrutinized the most is success-based fiber additions. If you needed to put the second scenario, if you needed to put all your 1,152 fibers in year one, you could blow all 4 288 fiber cables. You could pull all 4 288 fiber cables through the 4 conduits, and you're looking at a 61% increase in the traditional versus micro cabling systems. And that's a little bit of a wrinkle on, it's one 4-inch conduit with a segmented 4-inch conduit with a fabric called Maxcell. Again, that shows even if you put all the fiber capacity in year one, you're still saving significant cost with the microcabling system. On the next cost that's sometimes overlooked, but like I said earlier, it's bottom line cost. In a little bit, Anders will get to the environmental impact, and it kind of alludes to it here. But to get the same length of conduit and cable to the job site with the scenario 2, the 4-inch conduit with a Maxell interduct, the fabric, you've got that versus the success-based is 3 times as many trucks. But let's compare the scenario 1 that we talked about, success-based. You've got 4 trucks to get the 1.25 inch and the 288 fiber traditional cable to the job site versus 1 truck with the micro duct and the micro cable. So it's definitely saving 3 times as much gas fuel to get the materials on site. In addition to that, you can see the carbon dioxide emissions are far less, and we'll wait just a little bit till Anders addresses that part of it as well. Kind of a summary of what we just talked about, the total cost of ownership. It's material, larger cables need larger ducts, the micro cables need smaller ducts. Installation cost is a key component of the overall civil works. And the installation cost gets driven down by up to 50% with more efficient installation techniques, blowing micro cables in versus pulling traditional cables through conduits. Transport costs, we just mentioned that. And then the upgrade costs. You do not want to have to go back and absorb any more heavy equipment construction costs to upgrade your network bandwidth. That's where the microducts come in handy. A 4-way or 7-way, you have either 3 or 6 additional microducts in the future without taking on any more construction costs. And then, so just kind of a summary of that here in a poll question: what factors in the business case enable the least TCO? So I'll let the audience answer that. Okay, so this is good that we're not trying to increase splice points in the system. That's a very, very good answer. The rest of the 3 are definitely applicable to lowering the total cost of ownership. So very good answers there. Okay, so we would be remiss at Hexatronic if we didn't point out the fact that there are ribbon technology cables out there, some that can even be blown in, others are pulled in, but they're called flexible ribbons. So we want to point out some of the myths about micro cables versus rollable ribbons or flexible ribbon cables. Same thing, rollable ribbon, flexible ribbon. So traditional ribbon cables before rollable ribbons had a central tube, typically a central tube. It could have been a loose tube, but the original ribbon cables were a single tube, and you had a stack of flat ribbons, one on top of each other, like it's showing here on the left where the cursor is going across. Basically, a matrix would encapsulate 12 individual fibers, and then you were able to mass fusion splice 12 fibers together. That was kind of the leading benefit of ribbon technology back 25 years ago. Say rollable ribbons have been on the market for, it seems like 5 to 10 year time frame now. Don't hold me to that time, but it seems reasonable. But what you're doing with a rollable ribbon as opposed to the UV acrylate encapsulated ribbon on the top, the 2 in the middle are 12 fiber bound together at specific points, not encapsulated, but bound together at strategically specific points so that the ribbon can be rolled up. And if you can roll up a ribbon, you can get a lot more ribbon or fiber density within a given area of the cable. That's the benefit of a rollable ribbon, is a lot higher fiber density, and the cables can bend better. So that the ones that are out there that we see, not Hexatronic rollable ribbons, are anywhere 17, 28, 34, 56, and even up to 6912. All of Hexatronic micro cables are loose tube micro cables, no ribbons. But here's typically the cable technologies that get compared. You can see the range here. Traditional loose tube. This was the example we went through, the cables that get pulled through the conduits, up to 864, and you have a diameter range, a cable diameter range of 14 to 24 millimeters. You can see and so that kind of limits you on how far you can pull your cables through conduit with the weight of the cable. Micro cables that get blown through the microducts, much smaller cable diameter, much smaller weight, so the longer distances, all the way up to 864 fibers in an 11.7 millimeter cable diameter. That's the Hexatronic technology. The other two that have fiber counts up to 864, you'll have a single tube rollable ribbon, and the range on that we see is 10 to 20 millimeters, all dry tubes. And then the big ribbon cables, rollable ribbon, are up to 3456, 8 to 35 millimeters with dry tubes. So that's most of the documented comparisons that we've seen are between traditional, doing the comparisons between traditional loose tube fiber cables and these high fiber count rollable ribbon cables. So we got two claims here that we'd like to shed some more light on. The flexible ribbon claim one that you often hear is that splicing is 12 times faster. While it's true that you can physically splice 12 fibers simultaneously, 12 in a lot less time than you can splicing 12 individual fibers. Actually, it's not the fiber splice time that's the biggest factor. It's the cleaving time and things of that nature that actually takes to get 12 fibers spliced together. So that is very true. What also has to be considered in the overall time savings when you're using ribbon fiber to splice together, they're typically to dismantle and find the actual fibers you're in those high fiber count rollable ribbon cables. It takes a longer time versus the micro cables with the loose tube, where you know what color tube you're after and you can get your fiber out of there into the splice machine much faster. Ribbon splices in general, because they use fixed V-groove splice technology, have higher splice attenuation. And if the splice value is too high, you have to break it and reburn it. So that can take some additional time too. And there's also a fail rate. Anything when you're doing 12 things at one time, especially with precision fiber splicing to achieve the low loss, you're going to have fail rates, and you're going to have reburns as well. The last thing here, when you're in a mid-span type configuration in a rollable ribbon, that's called a unit with a unitube. It definitely takes considerably more time to extricate the fiber that you're looking to splice. So these four factors here have to be considered as well when you're just looking at overall splice time being sped up by 12 times. So to the micro cable, if you want to, they're loose tube cables like I mentioned earlier, but if you want to fiber splice those in a mass fusion way, 12 fibers at a time, there's a simple device, a very cost-effective device called a fiber organizer, and you can put 12 fibers in an organizer in the field and essentially make a flexible ribbon micro cable where you can mass fusion splice and speed your joining points up. Again, the goal is to reduce the number of these, but you're going to have to fiber splice micro cables together in the field once the either 4 kilometer, 6 kilometer, 8 kilometer reel runs out. And then the claim two, the higher fiber density. So it's not necessarily true for micro cables, loose tube micro cables up to 864 fibers. The range is 5.7 to 11.7 in the Hexatronic Viper line, whereas with the rollable ribbons, you have a range of 10 to 20 millimeters, both for loose tube ribbon, rollable ribbon, as well as single tube rollable ribbon. Kind of summarize the comparison between a loose tube micro cable up to 864 and the flexible rollable ribbon. Micro cables give you the best bending performance. They're truly flexible in all directions. A much smaller diameter, which means lighter weight, which means longer blowing distances. much easier to install, especially in existing ducts and where you have very limited space. And then the key thing here is just longer blowing distances. The machine and the air assist allows you to reduce your friction, and the small cables just ensure you achieve that 2 kilometer blowing distance. For the fiber cramp thresholds, on the other hand, for rollable ribbon, at 864, micro cables are definitely an advantage. If you get to situations where you have to put 6,000 fibers in year one, that's where an application would be in and around data centers. Those are fiber intensive, or a high capacity backbone where you have no choice other than to put over 3,000 fibers in initially. That could be an example where a rollable ribbon with a higher fiber count comes into play. But also consider even at a data center type application, if you could have your multiple loose tube micro cables in different pathways within the microduct assembly, you have a better chance of survival if anything were to hit the microduct. So that's another consideration as well. Last poll question. Pick the fiber splicing advantages of loose tube micro cable compared to ribbon fiber that are important. Give about 30 seconds for that. Okay, we got 33% response rate here. So definitely using the higher quality fiber splice machines, the lid, local injection detection, that is definitely an advantage. And reducing complexity is another advantage. So good answers there. Alrighty, Anders.
Okay, just a few slides left. I will talk a little bit about the environmental impact, as you mentioned before. And we at Hexatronic, we do have a software tool, which is called Mobius EcoChain, where we can use all the emissions from raw material to find the products. That's included in the tool and also the packaging. And we can make a life cycle stage from cradle to gate, meaning when the material coming into our plant, we produce a product and we put it outside the plant. The calculation has been based on the following data from our manufacturing in Sweden, and also from a database where we can get the data we didn't have available. And the comparison has been with a 1.5-inch duct and a 2016 microduct, and a 192 fiber loose tube conventional cable in the 1.5-inch duct, and a 192 fiber micro cable in the microduct. And this is a summary. During manufacturing, we can see that it's approximately 50% lower carbon footprint with a 2016 microcable system or microduct system. And looking at transportation, it's shipping and handling is approximately 63% less transport with the 2016 system. So it's a huge difference. Just a few words about the future for microcable systems, and it's not future actually, it's what's happening right now. If you look at the microcable that has normally been used in the middle mile and so on in cities, and as a feeder cable and so on, but in Sweden right now they start to use it as a transport network. You see a route there from north of Sweden down to Germany. Of course, it's submarine cables when it's a sea, but on the land, it's microcables all the way. And I took data from the cables that we delivered to this project, 75,000 values. and it's quite a generous standard for microcables because they are intended to be used in cities and so on. But you can see on the data there where you see that detonation at 1550 nanometer, 75,000 fiber measured, and that the detonation is around 0.18. So it's a very low detonation for this project. So we do have transport versions also of the microcable, and they could also be a little bit stiffer if you use it for this application, because it's many straight routes and so on.
Okay, so we're excited at Hexatronic about this new innovation called Viper Ease. That's our microcable line from 12 to 864 fibers. The large fiber counts, 288, 432, 576, and 864. Typically we'll have 200 micron fiber. It's after you remove the coating, it's the same G657A1 bended sensitive fiber as the 250 micron in the smaller cable sizes. But that's our line Viper, and heretofore they have been gel-filled buffer tubes, but now with the new Viper Ease, it's what's called a dry cable, meaning the buffer tubes contain no filling gel, and that saves your installer a significant amount of time after they move the buffer tube to splice the cables when that occurs. So it's the world's first and only micro cable with 100% dry water blocking technology. The core is dry, as well as now the buffer tubes are dry. That is significant. That line will be completely filled out this year from 12 up to 864 fibers. And then the technicians, like I said, that was the voice of customers from the fiber technicians needing more user-friendly micro cables in the field. Same performance specs with even further lowest costs. We're reducing the cost via faster prep time of at least 50% up to 70% with the Viper Ease versus dry gel buffer tube filled cables. So please ask us about that if you have any questions once you see our contact information. Here's just an example of the construction of the original Viper cable with gel filled tubes, superior blowing performance up to 2 kilometers uninterrupted, very, very high quality, long lasting materials that are rigid, as well as give the cable flexibility where it needs it for the bends. Even a very broad temperature range of operation, super low attenuation, and like I said, very flexible tubes whenever you need to bend the cable through the microduct pathway. The Viper Ease features is one at a time here. Basically, even in addition to the buffer tubes not containing the gel, they're yarn free now. The yarn doesn't have to be dealt with as well. Once you remove the jacket, the yarn goes away. Like we mentioned, a lot less cleaning, and then the colors are a lot more vibrant now in the tubes and the fiber and the markings to quickly identify fibers before you're ready to splice. So David, let's turn it back to you now for the formal Q&A.
Absolutely, and we do have a few questions that came in here, quite a few actually. So excited to get to those, but just for everybody's reference, if you look in that resources section again, you'll see that there's some videos and other information about the Viper Ease solution. So definitely check that out if you're interested. And let's see here. So going through, we have quite a few questions. To begin, what are the most common design considerations when deploying a microcable system to ensure durability and performance?
So it's a very good question. I think we hit on some of the components, but just to kind of summarize, when you're designing a mainline backbone or middle mile or transport or regional backbone fiber network, you need to understand over the life cycle of the system being at least 2 decades, 3 decades and longer, how many fibers that you anticipate may be needed in there. And try to avoid putting all the fibers in year 1 if possible. That's what a micro cabling system enables is incremental growth. But with that fill ratio that Anders went through of 40 to 75% being your highest performance in blowing distance and blowing speed, just consider if you, like, for example, if you know all you ever need is 576 fibers at a given location. Remember, we've heard that before, but if you're for sure that, for example, you need 576 fibers, maybe you wouldn't go into putting a 7-way 2016 microduct assembly in the ground. A 7-way 2016 could hold up to over 6,000 fibers, but maybe a 4-way 1612 would suffice in that case if 576 is the limit. So to answer the question is, you got to know your fiber capacity that you need through the life cycle of the system. And then you can size your microducts accordingly per the 40 to 75% rule that Anders went through.
All right. We have another here. What are the Hexatronic fiber distribution methods and how are they different from current fiber deployment methods?
So we've talked about micro cabling systems that the micro cables get blown through the microducts, say, for example, 1612, 1814, 2016 size microducts. When you get into the distribution of fiber to the home specifically, it's the same concept. You blow the fiber through the microduct system, but the microducts are significantly smaller. They're 7 3.5 millimeter microducts, thick-walled microducts, just like the middle mile ones that we've been talking about here. But that's how we distribute microducts throughout from the neighborhood demarc point called a fiber distribution hub out to the property lines. And then no fibers installed initially. And whenever the customers, the home's passed with microduct, when the customers start calling the ISP and ask for the service, extend the microduct through the yard, put the NIT on the side of the house, and then you have a home run 7 3.5 microduct pathway from your customer all the way back to the neighborhood demarc point. That's our distribution method. It's called ABF. The acronym stands for air-blown fiber, and that's how we reduce costs significantly versus traditional FTTH deployment methods within neighborhoods.
And along those lines, when talking about blowing the fiber, somebody asked if the drag and frictional properties of the microcable are important to blowing success, and how can you best achieve a balance between these properties?
Anders, you can take that one.
Yeah, if you look at friction, I mean, you use lubricant when you blow the cable through the microduct, and we also have some low friction in the layer in the surface on the micro ducts to decrease the friction. And regarding this, did you ask about the stiffness also? Or was it about the friction?
Yes, so they were talking about drag and friction in particular, but there was another question about the stiffness of the cables.
Yeah. So the stiffness is it depending on where the cable shall be used. If it's a cable that shall have been used in an application with many bends, then it will be less stiff than a cable that's for the transport network, for instance, where you blow long distances, straight routes, then it's big. They are more stiff, this type of cables. And we can balance that. We have learned that over the year. And since we also make both the ducts and the cables, we can always test them together. We cannot blame anyone else. I mean, we make the duct, we make the cable, we take responsibility of the long performance.
And well, we're talking about deployment and distribution here. Somebody's asked what equipment is required for microcabling.
So what was the question again?
What equipment is required for a microcable job?
I mean, you need some, cable installation machine like a mini-jet from Plumitas, a jetting V2 from jetting, mini-flow rapid from Fremco maybe, or from GMP. You have the Hurricane or Tornadoes. That's a machine you need. And you need air, of course. So you need about 220 psi of air and about 35 cubic foot per minute. So you need a compressor that can handle that. That's the two most important tools you need for blowing the cable.
So again, just talking about distribution here, or deployment rather, what are the main topological and environmental issues that decrease blowing distances?
Anders mentioned it before. I think, you want to let gravity work in your favor. So bends, there's going to be bends. I mean, you can't avoid bends, but you want to minimize them if you can. And then also the undulations, that's going to be a real world, microduct installation factor. But that's the lay of the land, so to speak, on that Anders went through, even beyond, staying within the fill ratio guidelines. It's just real world conditions that you're going to have to consider. And that like Anders said, our microduct and our microcables are tested together to reduce the drag or the friction whenever it's being blown through, as well as we have our own special compound for lubrication to lubricate the wall of the microduct prior to the microcable being blown through it.
So somebody's asked what the impact of microcables is on splicing. I know we talked about that versus the ribbon cables, but anything to add?
It's just it really it minimizes splice points, which is good for your network performance. Also saves money, but the splicing itself, whether it's 250 micron fiber or whether it's 200 micron fiber, it's all industry standard fiber ITU G657.A1. So it's the same fiber. There was one question in one of the poll questions: smaller fiber. There is no smaller fiber. Smaller coated fiber, 200 to 250, but the coating gets removed prior to fiber splicing. So it's all industry standard fiber. And micro cables, just like ribbon cables, just like standard all dielectric cables that get pulled through conduits.
All right, just looking through here. So somebody's asked a very specific question of whether you would recommend installing micro in a rural setting with less than 5 houses per mile.
So that's that question comes up a fair amount. The first typical in that scenario for like a traditional cable would be like a single jacket, single armor cable that gets plowed in a ditch. Just direct plow, no conduit at all for a rural setting. That's fairly typical for traditional. Whereas with the micro cabling system, we could install a 1410 millimeter microduct, for example, and then, or even a 7.3.5 millimeter microduct for that matter, to bring the cost down of the microduct. And the microfiber is only about 2 millimeters. You can get that anywhere from 12 to 24 fibers. So in the case of five homes per mile, that's what we would recommend is a 7.3.5 microduct, and then blow in a 2 millimeter nano cable is what we call it. So that would not be more cost than even a 12 fiber single jacket, single armor traditional cable plowed in.
We have a couple of questions just around the durability of the system. So somebody's asking how to ensure that a microfiber microduct system, since it's a thinner cable, achieves the same or even better long-term reliability and lifespan as more traditional robust cables.
I mean, we designed them for the same expected lifetime as a traditional cable. I mean, we have done tests in our lab and so on in temperature chambers under different conditions and so on, and it withstands. I mean, we test for 40 years, and it will withstand 40 years. And I mean, if you look at the duct, for instance, they have been around for so many years. We know it works, and the fiber, it's the same fiber as in other cables and so on. So it will have the same lifespan as conventional cables.
All right, and so I think this one might be a good one to end on. Somebody's asking if in the future microcables will be even smaller in diameter.
Yes, they will. There are some technologies that we not covered yet that are under development. For instance, multi-core fiber, where you have up to 8 cores in one fiber. So then you can reduce the size of the cable a lot and still have the same cores.
So yeah, I think that covers up for the questions. If we didn't get to your specific question here, we're just about out of time, but if we didn't get to your specific question, we do have them captured here. And so I'm sure the team will be following up with you. But before we move on from Q&A and just to the wrap up, I just want to hand it back over to Mark and Anders. Anything to add or any final words before we wrap up?
Greatly appreciate again Fiber Broadband Association for the opportunity to be a premier member and work closely with the membership here. We do, please email Anders or myself. We have should have our contact information here for follow-up questions. And thank you very much and have a great day.
Yeah, thank you everyone who were listening. Thanks a lot.
Yep, and so first, also thank you to Mark and Anders for taking us through everything. Very good. We still have, a lot of questions, a lot of feedback coming in, as you can probably see here. So really great, and even some an idea for a future webinar for you too that we can talk about. So appreciate everybody's time and attention today. We appreciate the fact that you're participating in these. It was great to see everybody last week at Fiber Connect, but we're certainly not done for the year. We have our regional fiber shows still in full swing. So we look forward to seeing you there. And I do understand that Hexatronic will be at some, but we're not sure which ones quite yet. But they were, I believe, in San Antonio. And did you say Richmond was the other one?
Philly.
Or I'm sorry, Philly. That's right. That was Philly this year that you were at Philly. So certainly look for Hexatronic at some of these shows. And if you're in the area of any of these regional shows, we look forward to seeing you there. We're going to be in Anchorage, Alaska. Very excited about that in mid-July. We'll be going up north again to Toronto in August. We'll be in Spokane, Washington in September, Scottsdale, Arizona in October, and finally wrapping up the year in Kansas City, Missouri on November 11th. So if you are in those regions, we look forward to seeing you there. These are smaller shows, a bit more intimate, and great networking opportunities. So definitely join us if you are able. Also, if you were on our Fiber for Breakfast this morning, you probably heard Gary mention the Fiber Rodeo. Part of our Optic Path team put that on at Fiber Connect, which was a competition with splicing fiber and some other things. It's a great program that we have. This Optic Path program is for training and certification of future fiber technicians. So we're always looking for feedback and interest in that program, and certainly volunteers. So if you are interested in volunteering and helping out or even teaching, use that QR code that you see there on your screen, or reach out to one of us, and we'd love to get you connected to that team. So look forward to hearing from anybody who wants to participate with that. And lastly, as always, I just want to wrap up by saying we have other webinars out there. As I mentioned, Fiber for Breakfast, we had that this morning, and that is every Wednesday. We talked about agentic AI this morning with Ron Westfall. So if you missed that one, be sure to catch that on demand and join us next week for Fiber for Breakfast. And again, that features Gary Bolton, our CEO and president, every Wednesday at 10 a.m. Eastern time. And of course, we have a lot of other webinars and other events too. Please go out to our website and check those out. You'll find all of that information under the events drop down at the top of the screen. But thank you all very much. We look forward to seeing everybody on the next webinar. Thanks.